Hello, I'm Shreya Gupta and I would love to explain about zk-SNARKs in a, in a modern world, how it's being used, mainly concentrating around the blockchains. So, in traditional blockchains, a transaction is sent to the network, validated at the first node, broadcasted to others, and eventually included in a block after proof of work, or say proof of stake or any other consensus. But now just imagine, instead of a system where transactions are sent to the network, forwarded to an external node, which might be say off chain, for processing, and only the result is sent back to the blockchain. The chain then verifies correctness instead of re-executing computations. So what all advantages we get for that? So we get scalability, throughput, and privacy. Scalability in a way that verification is cheaper than full re-execution, as we have sent the data off chain as well. Then regarding throughput, since only verification happens on chain. And for the privacy, sensitive data used off chain need not be published to the network. Hence, this is the motivation for using the zk-SNARKs. So the zk is a non-interactive zero-knowledge proofs which allow scalability and privacy. Proofs are short and non-interactive, as I said, and zero-knowledge ensures privacy of data used off-chain that and are not revealed. Verification cost is independent of computation's complexity. Verifying a complex computation costs the same as verifying a simple one. And the proof, a satisfying variable assigned for. Now let's see the broader value of it. So these are some of the key properties of the zk-SNARK. Argument of knowledge ensures the prover must actually know the solution to generate a valid proof. Okay, so before heading on to the setup or the broader overview, we can just have a pause and understand why zk is important, or where it is used, or what is its necessity. So it can be used for allowing privacy preserving transaction. They enable scalability in blockchains, more popularly in L1, L2, layer 2 solutions. Rollups have come up. There are various blockchains: Espresso, Scroll, Matter Labs, Mina protocol. The end of the presentation, we will be also exploring a blockchain of how the things are working there, or just a small application of it. So heading on to the heading on to the arithmetic part of it. So we see basically the computation is expressed as circuits in an equation, polynomial equation R1CS, which is then given to the set of phase, which generates providing key for prover and a verification key for verifying. Here the example is taken of multiplying two numbers. The prover finds solution and generates proof. The prover may reveal only the output, not the input. The verifier checks correctness without redoing the computation, and it's cheaper or like cost effective. We should explore the various setups. The transparent setup is one of the best, and then onwards, as you can see the downward arrow. All these trusted setups have been developed with time. So the trusted setup per circuit. Here, for every circuit C, a new setup is needed. Requires choosing random secret R. Here the problem is, if the prover learns R, they can create fake proofs. So this might not be much reliable, but back then Groth 16 has used it. Each circuit requires its own trusted CRS. Then is trusted but universal. Here it's the updated setup. So here, instead of redoing the setup for every circuit, you do global setup once. Here the randomness R is independent of the circuit. Then for each circuit, a deterministic algorithm derives the specific proving and verifying keys. These setups are often updated. Multiple parties can contribute randomness, so no single party is trusted. In this category lies Plonk, Sonic, and last one, the most updated one till now, is the transparent setup. Here no secret randomness R exists. Everything is generated deterministically from the public data. So there is no trusted setup, anyone can check the process. Here the example I would say is Stark, scalable transparent arguments of knowledge. So here it is being mentioned which kind of setup they have used, and we can see the proof of size is increasing, but there is not like a very drastic difference in the verification time. If you see how the proof of size is denoted or calculated, the proof of size grows only algorithmically in the size of the circuit. That is, even if the circuit is huge, the proof stays very, very small. And for the verifying time, the verifier runs much faster than re-executing the whole circuit. So basically, the proofs are very, very small. It's like logarithmic in circuit size, and the verification is very efficient depending mainly on the input size. So the verification is small even if the size of the proof is increasing. So here comes the general paradigm of SNARK. So paradigm is an imaginary word, but here it's an important concept of how I can say the blender analogy, or how the functional commitment scheme and the interactive oracle proof both blend in a way that the SNARK is formed. So what is functional commitment scheme? or say cryptographic object. So it is a cryptographic primitive where you commit to a value and later you can open it to reveal the value. You can take an example of an envelope, like sealing it in an envelope and later you can open it to reveal the value, ensuring both hiding and binding. Hiding in a way that nobody knows before you open, and binding in a way that you cannot change it later. The functional commitments generalize this. You can commit to a whole function or a vector or a polynomial representing computation and later prove correctness of some computation over it. So in zk-SNARKs, these are used to encode large structured data like polynomials, matrix, circuits encodings, so that the verifier can check claims without using the entire witness. And in the interactive oracle proof is a proof system where a proofer and verifier interacts. There earlier it was the dynamics of hiding and binding, and here it is about prover and verifier interaction. So in IOP, the verifier has oracle access to some committed objects like a polynomial, meaning that in a way that they can query specific locations rather than seeing the entire object. This makes proof efficient in terms of communication. They don't assume hard cryptography yet. They just ensure soundness if oracles are honestly implemented. So when I was saying it's a blender analogy, or they both blend in a way that SNARK is worked wonders. So I would say an IOP is not secure in practice because it assumes a trustworthy oracle, and a commitment scheme is not enough to provide interactive verification. When combining them both, they use the commitment scheme to instantiate the oracle in the IOP, the prover commit, the verifier queries, like this, and so on. This removes the need for trust in the oracle. And last, the result is in the cryptographically secure SNARK that works for general circuits. In short, I would say that SNARKs are constructed by combining an IOP with a committed scheme, cryptographically binding or hiding. This combination yields a system where the prover can convince the verifier of circuits satisfying with short, efficient proofs. Now here we are just looking upon the workflow of zk-SNARKs from raw computation perspective. So the first is the computation of circuits. We start with some program or computation. We want to prove knowledge. Let's say, for example, I know x such that fx equals to y. This combination is converted into circuit representation like Boolean circuits, arithmetic circuits. You know why? Because proof system reasons both algebraic objects more easier than arbitrary programs. And next is, and in the second step, you can see the circuit is translated into algebraic form. Let's say polynomials. So this process is called arithmetization. The example is R1CS QAP, the quadratic arithmetic program. More modern systems can be Plonk, polynomial, IOP. So the computation is now converted to system of polynomial equations. Third step is, or the third flow would be, once we have polynomial, we need a proof system to check them. This is informatic theoretic, meaning no cryptography yet, just theoretical soundness. So two families exist. PCPs. Verifiers can check correctness by sampling few positions, and IOPs. Similar but interactive queries. So now we need to turn this information theoretic proof into a practical cryptographic snark that requires compilation, and there are two main paradigms. QAP based snark, which is the trusted setup, compilation setup in a trusted setup, and the other one is PIOP based snark, polynomial commitment plus fiat shamir. The CRS arrows to QAP based means trusted setup required, and here the arrow means use random oracle model like hash functions with fiat shamir for non-interactivity. In a short way, I would say that start with computation and then represent as a circuit, and then turn it into polynomials or constraints, build an informatic theoretical proof, then compile into a cryptographic snark. Either your ways like trusted setup, CRS, or the polynomial commitments plus fiat shamir in ROM. So that's all the conceptual, or say to theoretical part of it. So now let's actually understand how it is implemented, and because developers don't write raw circuits, they use special programming languages designed for zero knowledge proof. That's called domain specific language. Example: Circum, Socrates, Noir, OpenJS, etc. These look like high-level programming languages but are built to compile down into circuits for SNARKs. So if we see the pipeline, it is DSL program, which is then converted to goes to compiler. There it is compiled into a constraint system that SNARK backends can understand. Backends in a way that, like EVM bytecode, so proofs can be verified by Ethereum, etc., and so on. So basically, DSL program is written in these many languages: Circum, Socrates, etc. The compiler converts into circuits, R1CS polynomials, and the prover, it's the backend part, the heavy computation with public inputs and secret witnesses, are converted into output proofs. and the proof with the short constant size, which is generator. I would say that it goes to the while file is there, which runs light computation over the inputs and the witness, and then the output can be that it will accept or reject it. That's how the code is actually implemented on the application side of it. So we will be looking on to two, two examples here of Socrates. One is Socrates and the other one is O1JS. Socrates is a high level language for writing off-chain computations, has been prototyped by other proof backends, and the other one is O1JS. Let me go back to Socrates once again. So here it is a domain specific high level language, the compiler that turns those programs into a provable constraint system from zk-SNARK. So here the tooling is provided are like the setup phase, witness phase, or say witness computation, then proof generation, then the solidity verification, export. So let us look at the example. Here it's in remix ID. I've written a very simple code of multiplying a number. Remix is an online ID where mostly developers use for writing programs and deploying on the Ethereum based chains. So here I have written the code. You can change numbers, no doubt about it, but for now I have written this. I have made a document to follow. So the steps are compile, setup, compute witness, generate, proof, and export verification. So to see the setup is, what is the setup? This one. We have to accept it. If you want, I can like cross it and we will see it again together. Neglect these both and just focus on root.zoc. So I will compute it first. You see the value true is mentioned, then we will do the setup. We'll accept it. A verification key.json is built. Then we should be going with compute witness. Maybe that we have already compiled. And you can generate proof. The proof is generated. We have to export the verifier. So here the verifier code is there. Here A is the private input and B is the public output as the keys. So we should definitely once compile it. Okay, we are getting a warning. We are getting a warning because we have not put this important line here. We should add this the very starting of Solidity code. The license line is PDX. Identifier D. Now it's compiled. Now if we want to deploy to the Ethereum chain, then it would be in another setup. We have deployed on the local chain. Now we'll go on to our next example. Also, Socrates, I have tried, I guess, implementing it via the terminals. Also, the same kind of setup is steps are used. First, we need to install it. Then we need to compile it and set up compute witness, and it's the same. And for the verified got passed, so it's verified. Now the other is this O1GS. It's of Mina protocol. Mina is a layer 1 blockchain, a 22 KB blockchain and zero knowledge smart contracts, zk-apps written in TypeScript. So basically what I am going to show you, or what you can try about, is that you can build and deploy a zk app on Mina protocol. Mina zk apps are special smart contracts that run off-chain proofs, keeping the blockchain lightweight. To develop or test safely, Mina provides Lightnet, a Docker-powered local testnet network that behaves like a mini Mina blockchain, or say small Mina blockchain. So let us try the tutorial. How can we interact? I've done the initial things of how to set up, how to test it and everything. So initially things had been installed, it's been set up, things had been tested, and I've pushed it onto the GitHub. Then meanwhile there was requirement of the Docker, so that has been done. So let us again go through some of the steps. So basically we are writing a zk app code and then test locally and then deploy to the lightnet. Your zk app runs on the local real blockchain and interact with it. Say the default setting. Let's see if things can work. Checking the Docker engine availability, prerequisites, stopping. If it be taking more time than usual, then I would be showing you my previous terminal of the VS Code and we will wrap up by understanding or getting through that as well. I hope I have better network connection. And yeah, we see the state, it's running true, kill false, and you can see all the status, endpoint, ID, consist configurations, start work fee. Okay, great. So there you can verify the status just in case. Now I think we need to do the config part. Config this C. Even though here this file had been created, as it's interacting what? Interact.ts. The config that we will create is interacting with config.ts. So create a name. You can name it. Sorry, you have to type here. Light net. This name already exists, so name Star Wars. Choose another schedule custom network. Provide a custom network ID. So I think this is Star Wars. Set a Mina GraphQL API URL. Deploy to. So we might get this here itself. Set transaction fee to use when deploying. Do we do 0.1 or let us try with this. Sure. So use store amount. So we have already created this alice.fee person, or we can select a different one. Let us try selecting the same one. Let's see how it goes. So next step, now it's about the deployment. So yeah, rest all the steps have been done. To see if this works. So we have issues with the fund. So we need to transfer some fund, or we need to change some code logic here. You have seen what I had created previously was lightnet. Right now with you I have created this. I guess the both are fee payer as both. We have made it same. Maybe if we would have made it differently, maybe things would have worked differently. So that's the thing, how we are interacting with the real life application based, how things are working. And there, apart from MENA protocol, there are other various blockchains as well, but I have taken this example. So that's it from my end. Thank you.